Let me know if you can see my screen.
Yes, we can.
You can.
But you can get full screen. We can see the full screen. Yes.
Very
Yes.
good.
Perfect.
Okay, very well. I'm going to start now. Well, once again, it's my honor to be a part of Xiamen University of Technology. And today I'm going to talk about complex dynamic system. I'm going to tell you what is complex dynamic system, and I'm specifically talking about tire road separation. But before going to the topic, I'd like to introduce myself. As you can see here, my current appointment is Professor of Mechanical and Automotive Engineering at RMIT University. And as you can see, I am Adjunct Professor of Xiamen University of Technology. I love this title. Well, I have very good memories from Xiamen University in the past before COVID. I was lucky to be there to teach a few classes, and you can see my photo in classes. Hopefully, it's gonna happen again. I was lucky to work with many universities. As you can see, American, Canadian, and Chinese university, and you see Xiamen University of Technology as well. Well, personally, I work in nonlinear dynamics, nonlinear vibration, very close with what Professor Dai is doing. Because of my job, which is a part of automotive engineering, I switched some of my research area to be related to automotive vehicle dynamics and so on. And what I'm working right now for a few years is mathematical definition of drift. And what is drift, which is very interesting topic, is this. I hope that you can see the video very well. This action of automotive is drift. And here you can see a very funny video which somebody with tractor controls very well. I'm sure that he doesn't know about mathematical definition of that, but he's doing very good job. Here is another video of drift. Most of them are sports drivers. And here you can see a fantastic maneuver. It was Raleigh in Kenya a couple of years ago. Here is one student. And here you can see another funny.
О, здорово. Здорово. Дрифтерская тусовка тут у вас? Да, тут. Ну туда перепаркуйся, там все стоит. Давай.
Drift is not just for vehicle. Drift can happen with motorcycle as well.
I'm coming in hot. I'm coming in hot.
Okay, maybe someday I'm lucky to give a presentation about drift. But today I'm going to talk about complex dynamic systems. By complex dynamic system, we mean a dynamic system that has more than one set of differential equations. More than one set of differential equations. And the system is switching from one set of differential equations to the other set according to some condition. Those conditions usually are non-polynomial constraints. I will talk about non-polynomial constraints later, but this is what I'm going to talk about. When the vehicle leaves the ground and it is flying in air, as long as it is in touch with the ground, we have a set of differential equations to study the motion. When it is off the ground, the differential equations are different. How we match these two differential equations and their solution is the art of mathematics. And today I'm going to talk about that in detail. This is what you see on tire road separation. It's easy to do the experiment and with the sensors measure whatever we want, but mathematical modeling is my focus today. This is what you see. A vehicle is moving over a bump and it jumps over the bump and separates from the ground. Here is an experiment. Okay. The first thing to derive the equations of motion. Let me explain what is the model. Please take a look on the left side picture A. Here we summarize, we simplify the model of vehicle as unsprung mass and sprung mass. Sprung mass, which is shown by M sub S. It's a sprung mass, means the mass of the body on top of the mainspring. Then below the body we have mainspring and shock absorber. Below them we have the wheel. Wheel is called unsprung mass, indicated by MU here. And then we have a very tough spring, which is symbolized for rubber, for the tire. And then we have the ground. Ground is moving up and down while vehicle is moving. Now, in part B, you see that it is possible, according to the amplitude and frequency of the road going up and down, the vehicle can leave the ground. Now, on the right-hand side, figure C, you see the free body diagram, which is very general. I'm sure that everybody means students are familiar with that. We derive the equations of motion by balancing of the total force equal to mass times acceleration, as you know the Newton method. So sprung mass has this equation. Again, sprung mass is the mass of the body. This model is called quarter car model. Quarter car model means we assume one wheel, one shock absorber and spring, and on top, one quarter means 1/4 of the mass of the body. It means one side, one corner of the vehicle is good enough to study the vibration. It's very traditional, very good model, and it is up to 90% accurate. Okay, after sprung mass, we go to unsprung mass. Now, here for unsprung mass, we have two differential equations. One for in contact with the ground, the other one for separation. As you can see, I indicated on the right side, bottom, in contact and separation. Look at the separation equation. On the right-hand side here, you see x0. And x0 here is introduced as mu plus ms, means total mass of the car, times g over ku. Ku was the stiffness of the tire here. I will talk about x0 and xt very soon. Xt is static deflection of the tire. Assume that the vehicle is just standing, no motion. Mass of the sprung mass, mass of unsprung mass together are pressing the tire. How much tire is going to compress? It's indicated by x sub t here. X sub t on the bottom, that's tire static deflection. And I'm going to use that very soon in next slide. To make the solution general for every type of tire, every type of vehicle, we have to non-dimensionalize the equations. Means make the equation dimensionless. To make equations dimensionless, we have to pick one for displacement, constant, one for time constant. Here, I'm using tire deflection, static deflection as x0, which is length, to non-dimensionalize the equation. And for time, I'm using a t0, which is inverse of frequency or natural frequency of prime mass. Based on them, I'm going to introduce new variables. Capital Y, which is road excitation. Capital U sub S is honest prime mass displacement, non-dimensional. And X sub S is prime mass displacement, non-dimensional. And tau is non-dimensional time. Based on that, static deflection of the tire now would be 1. So displacement 1 means deflection of the tire. Here, as you can see, x sub t, which is dimensional static deflection, divided by x0, which x0 is the same value, it's equal to 1. Okay, based on these new variables, we are going to have first and second derivatives, and then omega s, omega u are introduced here. Based on that, I'm going to introduce new parameters, alpha, r, zeta, and epsilon. Again, I remind you that we make equation non-dimensional. First of all, to make general means we study one vehicle, the solution would be applied for every vehicle. Second, we minimize the number of parameters. So non-dimensionalization is a very good step in studying in vehicle dynamics, not just vehicle dynamics. Absolute minimum number of parameters appears here. Again, look at the bottom. I have alpha, which is omega u over omega s. Look at omega u and omega s. When you divide them together, stiffness are in that alpha. R is excitation frequency, which is absolute frequency divided by omega s. Zeta is damping ratio, and epsilon is mass ratio. What mass ratio? Sprung mass over honest prime mass means mass of the body divided by mass of the wheel. The number of epsilon for my car, your car, street car is around 8. Epsilon is around 8 for usual car. For heavier car, it's going to be up. For lighter car, it's going down, but it is always between 5 to 10. Okay. Based on them, the equations of motion now are different. I have two sets of equations. First set, I'm talking about right top. First set is for in contact with the ground. The second set is for separation. Now we have the condition for separation and in contact or in touch. So my job is to solve these two equations and recognize when I leave the ground, I mean the tire leaves the ground, and when it is in touch with the ground. The condition for that would be xu minus y equal to 1. Less than 1 is touch. Greater than 1 is separate. What is that? xu is displacement of the center of the wheel. Y is the displacement of the ground. If the distance between center of the tire and the ground is relative displacement is more than static deflection, I'm losing the contact. So it is very easy to explain. I'm going to use Heaviside function from mathematics. I'm sure that you are familiar with Heaviside function, which is a mathematical definition of switch in mathematics, off and on. Using Heaviside function, I'm introducing S, which is a contact variable or separation variable. I'm going to use that later. So far, I have two sets of equations and one condition to switch between two sets of equations. Okay? Now, let's study frequency response first. And I'm explaining why frequency response first. For frequency response, you are familiar that we assume that the input, in this case the ground, is moving up and down with constant amplitude and different frequency. I'm going to change the frequency later. So frequency is unknown. It is harmonic excitation. Based on that, as long as we are in touch, we are going to have harmonic response. So I'm assuming y is y0 cosine of omega t, and in non-dimensionalization, it's y0 cosine of r tau. Based on that, we get x prime, x double prime substitute in the equation when we assume that they are in contact. And then we get the solution, and these are unknown coefficients of xs and xu. Based on them, what we need is the frequency response. Here is the frequency response. Look at the second set of equation. X sub s squared, x sub s, here is frequency response of sprung mass, and x sub u frequency response of unsprung mass. As you can see, Z1, Z2 are two short notations that we substitute there. So analytically, we are able to calculate frequency response as long as the tire is in touch with the ground. What does it do for us? We can show the frequency response of a quarter car. So far, everything linear. There is no nonlinearity. There is no separation. Is this frequency response correct? Depends on separation and non-separation. And I'm going to show you that not all of these frequency responses is correct. We are supposed to detect what part is wrong, and we solve that. Okay. Separation limit is here. Let's define a new variable called separation limit, x sub t. X sub t is relative displacement of unsprung mass and the rho, means tire and the rho. The difference between those displacements is measured by x sub t here. So when x sub t is more than 1, we have separation. When it is less than 1, we have non-separation. Let's find the frequency response of that one, and you can see here capital X sub t. Here is the equation, and I'm going to plot that. Now look at this graph. You have to focus on the black line, but to get rid of the blue and red, I explained that. The blue is frequency response of sprung mass. Red is the frequency response of unsprung mass, means wheel. Forget about them, just look at the black one. The black one is relative displacement of the tire. So as you can see, the black one up to around 7 for R, we are less than 1. As soon as the black one touches the line of 1, we are separated. So that frequency response for the red one and the blue one, after the point that the black one crosses the line 1, is wrong, because that region is the separation zone. So exactly I show here what part is not correct if separation is allowed. Now we have to study the motion of the system for different parameters. This is another frequency response, and as you can see here, separation can happen in two different zones. One close to the first natural frequency, and second close to the second natural frequency. Okay. So far we studied that we are able to detect what part of the frequency response of the system can be wrong. Let me define separation function. Xt, which was relative displacement, divided by amplitude of the excitation, is equal to that function. Whenever this function is equal to 1, we are at the border of separation. Okay, I'm going to plot this like that. Look at this curve. Horizontal axis is frequency. Vertical axis is alpha. Alpha was omega s over omega u. And these curves that you can see, look at the red one. The red one is that separation function. Below that, we have separation. Above that, we are in touch with the ground. Okay? Now, let me show you how we use that graph. This is another graph for different value of epsilon, which is damping. Let's assume that we have zeta equal to 0.4. Zeta equal to 0.4 is this one. This line is zeta equal to 0.4. And let's assume that alpha is high value, something around 5. Okay, 5. So from 5, I go to the right, until that point that I touch the curve for separation associated to 0.4. At this point, from the right side, it's unacceptable. Below that, we have separation. We can do the same thing for alpha equal to 3, and you can see that we touch the curve of zeta equal to 0.4 as 1, 2, 3 points. And separation happens below that. In touch happens above that. Okay? Now let's see some examples for real car. These are some numbers, usual car. These are actually for my car, which I am driving, a Ford Mondeo. For these numbers, we get epsilon 8, zeta damping ratio 0.3, alpha equals to 9 point something, and we have a bump. Bump is usually modeled by sine square, and S means separation function is here, and here I'm going to study over a bump. Let me explain what we get here. Look at the blue line. Blue line is Y. Y is the bump. So there is a bump on the ground. It is not in a scale, so vertical axis and horizontal axis have different dimensions. It's a very shallow bump, 10 centimeter high and around 30 centimeter wide. Now look at the black line. The black line here is unstrung mass, means the wheel displacement. The red one is sprung mass, means vehicle vibration. Now there is S. Look at this, S is 0, here jumps to 1 and then jumps back to 0. Wherever S is equal to 1, we have separation. So S is separation indicator, the same thing that I mentioned, I use Heaviside function for. So S is a switch. When it is 1, separated. When it is 0, in touch. Now look at this brown curve, which is XU minus Y. And I'm going to explain more later on. Here, I wanted to show you that S function is a switch to indicate when we have separation. Okay, let's look at a very interesting maneuver. Let's assume that the vehicle is driving and it is going over a ramp, and then ramp stops and it is jumping over the ramp in air. Model of that would be like this. The car on the left side is moving velocity v, going over this ramp. The ramp has a length L, height h, and then after the ramp, the car doesn't have any choice. It must jump and separate from the ground. Let me introduce a new function, capital Z, which is displacement of the below of the tire. Very interesting variable. Displacement of the below of the tire. Okay? Now these are model mathematical definition of the ramp, and as you can see, the ramp is just a function of time, and after reaching that time, it's going to be separated and the ramp disappears, and this is the response. Very interesting curve. I'm going to show you or explain very well. First of all, look at the blue line. Blue line, this blue line, which this part you see green. I explain why it is green. The blue starts from here, goes up to here, jumps here, and goes horizontal. This is exactly the same ramp here. Again, this graph is not in scale. So don't assume that the ramp is very high. It's very shallow, and I explained what is the length of that. I think 10 centimeters by half a meter. Okay, now look at the black line. Black line here is the displacement of the tire, center of the tire. Look at the red one, which is displacement of the body of the vehicle. Look at S function, which is the switch for separation and unseparation. As you can see, right after the ramp, we have separation for a while, and then the car touches the ground. So we have, for a while, this long horizontal axis is time. For this time, we are separated. Now look at the green line. The green line is the variable Z that I explained above. It is the displacement of the below of the tire. Now, when the vehicle is on the ramp, below the tire, the touching point is on the ramp. That's why the green and blue are the same here. Right at the tip of the ramp, the tire will expand. So this little jump here in the blue shows that the tire expands to the original length. So static deflection disappears. Imagine that we assume that displacement of the springs happen in no time. We do not assume any time for that. And then after that, look at the below of the tire. Below of the tire is following the same pattern as the mass, as the center of the wheel. So below of the tire is the green one is following the same pattern as the black one, which is the center of the wheel, and then comes down and exactly at this point touches the ground and sticks to the ground. Very good, very interesting. As far as I see, all the mathematics are working very well. We are able to analyze the system when it is in touch with the ground. We can study the system when it is off the ground. Now, what is the purpose of that? The study will go into the frequency response and see what part of that frequency response at the beginning was wrong. That's the goal of this study. So to be able to do that, we have to study harmonic response. Harmonic response is like this. Means the vehicle is moving on a wavy road. When we increase the speed, it means the excitation frequency is increasing. So we assume that amplitude is constant, but velocity is going to be changed to change the frequency. And this is the equation. As you can see, for frequency of this wave, we have velocity. So velocity is associated to frequency. Okay. One example, numerical value, and as you can see, W, 0 to W is wave length, which is pi over 5 meter. It's a very big one. Velocity 10 meter per second. Displacement, static deflection of the tire is around 1.5 centimeter. T0, which was constant time, not important to us, is that much. Look at the graph. The graph, again, is very interesting to me. Look at the blue one first. The blue one is the wave on the ground. Again, it is not in scale. The black one is displacement of the center of the tire. So blue is the ground, black is the center of the tire. Red one is displacement of the vehicle, the body. I will talk about that later. What we are going to look at is the green one. The green one is Z and displacement of the below of the tire. As you can see, let me start from here. The below of the tire is stick to the ground at this point, still stick to the ground up to that point. And as you can see, we have separation. This point will be separated, jumps to the other one, and then follow the second bump, jumps to the other one. So the tire will not touch the bottom of the well here. Going over this bump means going over this, jumps to this point, follow the other one, jumps to the other one, and so on. This displacement, which is shown by green, is fantastic variable, explains everything. Now, when you see this graph, we may assume that it's a steady state after a while. But let me tell you, it's not a steady state as long as all variables show steady state. One of them, which is XS, displacement of the vehicle, is still going up to show that later on I show that it takes more time to see a steady state. But before going there, let me change the velocity and see the same thing. This is another velocity. Where is the velocity? Velocity is in R, frequency. So when I say we increase the velocity, means we are increasing the excitation frequency. Okay, here you can see the red one. So it takes a long time to see a steady state. Look at the first picture on top left, and look at the horizontal axis. It's 2 time unit. 2 time unit. On the right side is here, between 0 to 5. And you can see that the very short term, we cannot see a steady state. But if we give enough time, look at the frequency response on the right-hand side. It's actually time response, but you can see that it's going to have steady state vibration. So we have to wait, at least in this case, up to 30 time constant, 30 unit of time to see steady state for vehicle. So our job is to do that. Let me review the harmonic frequency, harmonic response of the vehicle for different velocity. That's a very small, short velocity or small velocity. As you can see, R is 0.6. We have separation, yes. Look at this point. The S shows a jump, but later on, for that little frequency, after transient, we have a steady state in touch with the ground. Change the velocity. Now we have separation. Look at the indicator of the separation, so you understand that we have separation. I showed everything. We can go into the detail, but it's self-explanatory. So as you can see, velocity change, so frequencies change. Higher velocity. Beautiful graph. Very beautiful graph. We can study every little of that. My point is that one question comes to the picture. Is it possible that the vehicle jumps over one bump and sits on the other bump? Means one jump, one of those bumps totally skip. I'm going to increase the velocity and see if it is possible, and our mathematical model can detect that. Higher velocity, and what you are looking for to notice is the green one. Okay? Higher velocity, and look at the green one. And here is another. And finally here, look at the green line here. And here the vehicle is totally jumping over one bump and sitting on the third bump. That's very good, because I'm happy that mathematical model can detect this type of strange behavior. Okay. Now I want to find the frequency response and detect what part of the frequency response was wrong. And to do that, we trust time response. We give enough time until it is settled down. Here, you see that after 100 units of time, it's almost steady state, at least by visualization. Mathematically, we have to detect the peak value of at least 2 of the peaks next to each other, and if their difference is within the limit, for example, 0.001, means one out of 1,000 difference, then we accept that it is a steady state. So we adjust a tiny value to accept that it is a steady state. In that case, we pick the value of the number, and then we change the frequency. We wait until it is a steady state. We detect the peak value again. We put them in a matrix, and then we plot that. We assume that it is frequency response or close to frequency response. And this is what we get. First of all, you're familiar with this graph that we had separation. Now look at the blue one, which is displacement frequency response of sprung mass, means vehicle. As soon as it goes to the separation zone, it jumps and it shows very interesting behavior. Our key point is the black one. Black one, as you remember, was relative displacement of wheel respect to tire. As soon as the black line touches the line of 1, we are separated. Now, how we detected that? Again, we trusted transient response, waiting until it is a steady state, and then we detect the value, and we make an array, and we show it. This is a better graph. Here I showed the linear and nonlinear frequency responses together. Let's assume that separation makes everything nonlinear. So look at the dashed line. The dashed line are linear. Means assume that the tire is stick to the ground. The solid line is separation. First of all, look at the left-hand side before going to the separation zone. As you can see, on the left-hand side, analytic solution and numerical solution are exactly the same. So it gives us enough confidence to trust the value of detection of amplitude for the separation zone as well. Now look at the solid line in the separation zone. For example, look at the solid line red and dashed line red. The dashed line is frequency response of the unsprung mass, and the solid line is the actual one when we consider separation. That's all I wanted to say. So what I did was study one complex dynamic system, means a system having two different set of equations. And then my goal was to find out if we are able to develop a mathematical model to study this for separation, touching, jumping, and design or detect the frequency response differences. I'm done, and thank you very much for listening, and I'm open for any question if you have. Thank you very much.